let them know you know that we had a little glitch and go on, I guess. All right, I'm out of here. I mean, it's.
Okay, Tamara, we had a little hiccup in the system. We're trying number 2. Tamara, take it away.
Okay, welcome to the Astronomy Club of Tulsa, all you new members. We're delighted to have you. As members, you will have many wonderful opportunities to join us in observing the beautiful night sky and make new friends and lasting memories for you and your families. Plus, there are many opportunities for public outreach to get others interested in our hobby. Also, please feel free to ask questions, offer suggestions, or volunteer to help out at our events. All new ideas are welcome, and we're very glad you're here. We're so glad to have you. Next slide, please. Okay, this is where we had the glitch, and I apologize to all y'all. I guess it kicked everybody out, and we all had to start all over again. Unfortunately, due to the present health risk, there will not be an annual dinner meeting this year. We may plan something for next spring if the pandemic is under control by then. And also, please observe guidelines that we have set forth for our observing nights. Our general meetings will be held via Zoom for the remainder of this year, and dates and times are to be announced. Okay, next slide, please. Guidelines for our observing nights. Set up your equipment at least 6 feet away from each other and remain at least 6 feet away from each other. We encourage the wearing of masks if you wish to chat with people. Please exercise proper hand washing and sanitizing. There will be soap and hand sanitizer in the bathroom. Classroom is only open for access to the bathroom. All other areas are off limits and the dome is closed. No sharing of equipment. There will be some club telescopes that members may use with designated eyepieces. These will be sanitized after each use. No children under the age of 12. All children must stay with their families at all times. And finally, relax, enjoy yourself, and have fun. Next, please. We have a private Facebook group just for Astronomy Club of Tulsa members. And James, do you want to go ahead and present that to everybody?
Yeah. Let's see here. Is everyone able to see my screen, or did the sharing stop? Can you hear me?
Yeah, I hear you.
Is my screen still sharing? Oh, it didn't. It does not seem like it did. Yeah, I just wanted to remind everyone that we do have a Astronomy Club of Tulsa members only page. We've got about, I think, 52 members out there right now. If you're not on it, please go ahead and join it. We'll hopefully have a little more interactivity on that site. And if you've got any questions or anything, post up. And there's always people out there that will help you with your questions. So just it's a good resource, and we'd like to use it as much as possible.
Okay.
John Land, do you want to do your video?
Yes, let me get my share screen here. This will stop screen sharing.
Yes.
Type yes.
Yes.
Okay, where is my PowerPoint? There it is. And we'll start right here if I can get it to go to the right slide. Okay, can everybody see that?
Yes.
Yeah.
And try to bring it up a little bigger. There we go. Of course, today is the first day of autumn. Autumn officially started this morning at 8:31 a.m. In fact, I was watching Channel 6 News, and they had a little clever countdown to the beginning of autumn. But the question is, how do we know when fall actually officially begins? Some years it might be 95 degrees this time of year. So how do we know when autumn begins? Well, autumn begins when the sun is exactly on the celestial equator. You can see this right here. I don't know, guess you can see my cursor, can you? On the left of my screen, you see the sun on the celestial equator, and the yellow line, the ecliptic, is the path of the sun. So when the center of the sun is on the celestial equator, then it's the beginning of autumn. On the right-hand side there, you can see that autumn begins now when the sun is in the constellation of Virgo, just toward the top of the head of Virgo. Here's a couple of 3 little slides that show you where the sun is on the winter solstice on the left. It's way down low below the equator, 23.5 degrees, in the edge of Sagittarius, more or less where the Lagoon Nebula and all that stuff is. Then it comes back up to the springtime when it crosses, we call that the vernal equinox, and it's in the western part of Pisces, near where Mars is now, underneath the Great Square. So there it is there. And then in the summertime, it's quite high up in the sky. And well, it officially crossed into the borders of Taurus, the bull, in the late 90s. So it's now in Taurus instead of Gemini. So it's up high above the equator. So here's a little video if it'll work. We're starting out with autumnal equinox. There's Leo there at the top. It's on Virgo. The red line is the equator. The green line is the path of the sun. We call that the ecliptic. And hopefully this little movie will work. It's got a little stall to it, but he'll get going here, I hope. There we go. See the sun going lower and lower each day. And down through Libra and the top of Scorpius, and spends a couple of weeks in Ophiuchus. And it gets down here to the winter solstice. And then it heads back up through Capricorn and then Pisces, and makes this little figure 8 pattern.
Oh,
Up and down, up and down.
that's cool.
Now what I've done, I've got it set more or less for local noon. And that figure 8 pattern's called the analemma.
All right.
The sun runs a little fast in November, a little slow in February, high in the summer, low in the winter. So sundials were not very accurate. I think there's like 34 minutes difference. But we'll talk about analemma another time. Sure if this is the same movie or not. I think I had 2 of these. I was having all sorts of issues with my computers. It's pretty much the same thing. Goes down into Ophiuchus, stops at the winter solstice, comes back on up through Capricorn and Aquarius, and does this little zippity-doo-dah thing.
Cool.
All right, the star of our October skies is Mars. And 2008, Mars was 18, excuse me. Mars was a little closer to us, but Mars had a global dust storm. We didn't get to see much. Well, Mars is going to be closest to us on October 6th this year. It's at opposition on the 13th. Mars is looking good, but we've got the smoke storm now. So. These little numbers down here, it looks like 10 inches and 12 inches. Those are what we call arc seconds. An arc second is 1/60th of a degree. So 22.6 arc seconds. That's pretty big. I looked at it the other night. It's considerably bigger than the disk of Saturn. So wasn't very good to look at through the dust, but I could make out a few details. Here's a little video that starts out last September when, well, actually August, I guess, because the sun's in Cancer. And we're going to watch Mars as it moves across the sky. It takes about 2 years to go around. Here we go. So here comes Mars through Virgo and Libra and down into Scorpio and Sagittarius. It also follows ecliptic, but not exactly on it. Now take a look what's going to happen here.
Oh. Uh-huh.
So what's the deal, Lucille? Why did it bar it back up? What was that guy on Channel 6 used to say, hey, what's the deal? Well, what happened is Mars is losing along in its orbit like it normally does. But we caught up with it and passed it. That's called retrograde motion. Like you're passing a car on the freeway. It looks like it's going backwards, but you're both going the same way. So it keeps on going, and you'll notice that it goes past Cancer and Leo and gets clear over into Virgo before the sun catches up this next time. So that's one orbit of Mars in relationship to the sun and the Earth.
That's cool.
And so what does that mean when we're looking in the telescope? Here's Mars like it was last September. And I'll run this thing. It takes a little while to get going. And as I'm running things one day at a time. And you can see that Mars is zooming in, getting closer and closer. Mars has phases, kind of a gibbous phase.
Wow.
There's where we're going to be in October. Pretty big. And then through November, December, and then I think it ends in September next year. Not much to see way back there, so. I think I've got one more slide. So here's the orbit of Earth in blue. We're almost perfectly circular. We're like 0.07% out around. But Mars is 0.94 eccentricities, almost 10% out, not 9.4, excuse me. It's almost 10% out around. So you can see over in 2018, Earth and Mars were pretty close. We're still pretty close in 2020, but it'll be 2035 again before Mars gets this close to us again. You notice there in August on the Earth line, when Mars and the Earth were closest together, that was back in 2003. We had a really, really close opposition that year. So get out and see Mars this month, because some of us won't be around in 2035. All right, I'll see if I can get off here and let everybody else do their thing. There you go.
Okay, I think I need my PowerPoint up again so I can see what's next, because my memory isn't worth poo-poo right now.
Yeah, just time for Robin to give his presentation.
Okay. Tonight's presentation will be given by club member Robin Jones on electrically assisted astronomy. And Robin, take it away.
Okay, can everybody hear me all right?
Yep.
I am going to put up my presentation. Hopefully everybody can see that. I'm going to go to full screen. Okay. All right. So I want to talk tonight about electronically assisted astronomy. And this is a presentation that was put together at John Land's encouragement back in June. He contacted me and told me that he had purchased a Revolution Imager CCD camera and knew that I had been using Malin cams for a few years, and he wanted to come over and see what I was doing. So he came over one night and we set up my equipment outside, and we ran the control wires into my house, and he sat on the couch in my den, and we looked at DSOs, deep sky objects, on my big screen TV, and he had a soft drink in his hand, and we had a good time together. So, and afterwards he said, would you be interested in sharing what you're doing with our club? And I said, sure. So that's the genesis for this presentation tonight. Before I get going, I'd like to thank 4 people for their encouragement and suggestions. I mentioned John Land earlier. My wife, Rosalind, who's also a member of the club here in Tulsa, Mark Faraz of the Houston Astronomical Society, and Sven Schmidt of the Longmont, Colorado Astronomical Society, and he is on the meeting tonight. So with that, we'll get going. So I'm going to talk about what is EAA, or Electronically Assisted Astronomy, talk about why I started, how I got into it, what are the benefits, what paths can you pursue with this aspect of the hobby, what are the equipment prerequisites that you need, what are the basics of the equipment, what are the challenges, what affects performance. I'm going to talk about the equipment that I have. I'm going to show some sample images from different cameras, and then I'm going to provide some resources. And I think John Land has that list of resources, and the resources is just some websites, some articles that were in Sky and Telescope that talk more about this in detail. And then we'll have a Q&A. If you do have questions during the presentation, if you would, just type them in the chat box, and I will try to take all the questions at the very end. I'm sure that there'll be some questions that aren't covered as I go, but I think a lot of the questions you may have should be covered by the end of the presentation. So what is EAA? EAA is astronomy assisted by analog or digital cameras that can provide images in real or near real time. In other words, a few seconds to a few minutes. In essence, the traditional eyepiece is replaced by the camera and a display device. The display device can be a small screen, it can be a 10-inch LCD screen, it can be your computer, it can be an analog TV monitor, it can be a big screen TV. There's lots of choices. There is a difference between a true video camera and a digital camera, and that is a true video camera can produce an image independent of a personal computer or a computer, and it doesn't require any post-processing to produce an image, whereas a dedicated imaging camera requires software and a computer to make it work. The cameras range from simple, very low resolution surveillance cameras of 0.5 megapixel to very high resolution cameras as high as 26 megapixels. And the higher end cameras can stack images, can subtract dark frames and flat frames on the fly. There may be some imagers on the presentation tonight. If there are, please be merciful to me, because I do not claim to be an imager, but I do claim to be someone that has fun with cameras. So as I said a minute ago, some cameras require a PC to run them and some don't. A true video camera doesn't need a PC, and those typically have buttons on the back of them that you can use to access a menu that's internal in the firmware of the camera where you can control exposure time, gain, gamma, etc. And I will show some examples of those cameras later. There is another part of EAA, and that's based on night vision technology. When I was in Kenton, Oklahoma last week for a very small private star party, a friend of mine had a night vision ocular, and he showed me the Crescent, the Horsehead Nebula, the Veil, the North American Nebula, and the Pelican Nebula, and it was just amazing how quickly you could see things. It was just right there in the eyepiece. So it's very cool stuff. I believe Dennis Burney, a member of our club, had a night piece ocular either last year or the year before, and he showed me some things with it's very cool stuff. Very cool stuff. And before I leave this screen, can anybody tell me who this guy is right here? That would be Steve Chapman, taking a little snooze, looking through some binoculars, I think. So anyway, let's move on. So why did I start? I started because I could not see a lot from my backyard, and I wanted to be able to see more. So these cameras I had read about would allow you to see quite a bit more from your backyard. I kept reading about them, and I wondered if it was just too good to be true. And if you look at this, map, this is a dark sky map. I think it's a few years old, but the general concept is still the same. You can see that the club's observatory out there in Mounds is out there in the green zone, kind of on the edge. You can still see the Milky Way there at night. It's not super bright, but it's definitely observable. Whereas you move about 20 or 30 miles away, here I am in suburban Broken Arrow. I'm 1 mile to the east of Memorial Drive, a Super Walmart, a Costco, a Reese's. I think there are 4 car dealerships another mile to the north. My skies are Bortle 9 skies. On a good night, I can see Mu Andromeda, which is about 4th magnitude. Most nights, if they're fairly decent seeing, I can see Alberio naked eye with no problem. But I wanted to be able to see more from my backyard, and I didn't want to have to go to a dark site to be able to do it. So I started because I do admire the images that astrophotographers take, but I don't have hours or days to take one image. I was looking for something in between, something that would allow me to see deeper, fainter objects. And if I wanted to take a little picture, I could, but I didn't want to spend hours and hours or days taking a picture of one object. I wanted to make the most of my observing time, and if I wanted to take a picture, I wanted to be able to do it in minutes, not hours. So most of the image that I capture range from anywhere from a few seconds to maybe 10 minutes. I think the longest I've ever done is 25 minutes. But most of them are on the order of 10 minutes. I've always liked technology, and I enjoy the satisfaction of solving challenges, of making different technologies work together. So combining the desire to see more in a suburban backyard environment with the scope that I have, and combining that with the cameras that are available, this EAA fills that gap for me. And on forums like Cloudy Nights, they make a very big distinction between EAA and astrophotography. They see them as very distinct and very different. But I would argue in some cases that the lines between astrophotography and EAA tend to blur very rapidly. And on the right-hand side of this slide, you'll see some images that I've taken. At the top is a double moon transit across the face of Jupiter with a great red spot. There's Saturn, and at the bottom is Comet Neowise. And all of these images were taken from my backyard. And with few exceptions in this presentation, all of the images you're going to see, and I will tell you which ones were not, were taken from my backyard. So what are the benefits of EAA? You can see a lot more detail, you can see deeper objects, much fainter, and you can see color. And I really have trouble seeing color with my eyes. I'm amazed at how some people can go up to the telescope and they can say, oh yeah, it's this color, that color. Most of the time, all I can see is black or white or gray or somewhere in between. Now, for a brightly colored star like Alberio or Herschel's garnet star, those are obviously kind of a deep orange color and you can see those. But for most deep sky objects, I just don't perceive any color. One of the things I really like about EAA is that you can enjoy it out of the elements. You can either be in a tent, or you can be inside, you can be under an awning, you can be away from mosquitoes, wind, cold, etc. What's really nice about it is you can show other people what you're seeing and you don't have to fiddle with focus, changing the focus for someone else, telling them where to look, etc., telling them what to look for. It's usually very obvious on the screen. And with a video grabber, even with a simple camera, you can snap a picture, kind of like a screen capture on your computer, of the image. And while they may not be Sky and Telescope worthy, in other words, it's not going to show up in next month's issue of Sky and Telescope or Astronomy Today, they can still turn out pretty decent images nonetheless. So there are many paths that you can pursue with EAA. You can observe things on a monitor or a PC. You can take screenshots. You can take longer stacked exposures. And with the higher quality cameras, you can actually do very good high quality astrophotography. You can also take videos of eclipses, occultations, transits. You can do planetary imaging and stacking using what I call the lucky imaging technique. And I'll talk a little more about that later. One of our club members, Skip Whitehurst, used video cameras to participate in an occultation project. It was either last year or the year before, where they set up a series of video cameras and small scopes over a planned path of an asteroid, and they were looking for star occultations to be able to determine the size of the asteroid, and that was done with video cameras. The last thing that you can pursue with a video camera is spectroscopy. In other words, you can analyze the star and object emission and absorption lines to classify what type of star it is. And you can also calculate redshift. Now, you do have to buy separate software for that. And at the end of the presentation on the resources page, I provide a link to a vendor that provides the diffraction grading and the software that you would need to be able to do that. So what do you need? Just the basic prerequisites. You need a telescope, you need a go-to tracking mount, and a tripod. If you want to capture images, you need a computer. You can control some cameras with buttons on the back of the camera, but I think if you do this very long, you'll rapidly decide that you want to use a computer. And most people today in the hobby have a laptop, and most laptops are sufficient to run the programs that run the cameras.
Wow.
Someone is not muted, so I would just encourage you to mute until we get to the Q&A session. Equipment basics, there are two types of cameras. There's a CCD-based camera and a CMOS camera, and we'll talk more about that in just a minute. One thing I'd like to point out is a decent camera can effectively increase the aperture of your scope. Obviously, it doesn't change the physical size, but because the camera is so much more sensitive than your eyes, it can see things that you cannot see with your eyes. The faster the focal length of the scope, the better. So something in the f4 to f6 is better than f10 unless you're doing planetary. And the lower the focal length, the shorter the exposure time for any particular image. I am running one scope at just under f5, and I'm running another at just under f6. You can use an Alt-Az mount, but a German equatorial based mount or an Alt-Az with a wedge is preferable. To save images, you're going to need a video frame grabber or software. The thing about cameras is they're very similar to eyepieces in that the larger the sensor, the larger the field of view, the smaller the sensor, the smaller the field of view. The last thing that's very important about a camera, just from a physical aspect, is that pixel size affects the sensitivity. The larger the pixel, the more sensitive they are. And we'll talk about that in more detail in just a minute. So there's basically two types of cameras: a charged couple device and a complementary metal oxide semiconductor device. They each have their advantages. I will say that most of the new cameras that are coming out today are CMOS-based cameras, and kind of the short reason for that is that CMOS chips are the most prevalent chip used in cell phones and other types of video technology today. CCD devices are becoming less and less available. CCD devices are more prone to what's called amp glow, which means at high amplification of the signal, you will see a bright region in the image, and all that is an artifact of the electronic amplifier on the chip working hard to amplify the signal that each pixel is picking up. With a CCD, each row of pixels is read off one at a time and then runs through one amplifier, where with a CMOS-based chip, each pixel has its own amplifier. I want to talk a minute about binning. And binning is just a technique where a camera can combine adjacent pixels to turn it into an effectively larger pixel. So for example, if you go from 2x2 binning and your pixels are 4 microns in size, by doing 2x2 binning, you have a pixel that is 8x8 microns in size. So you have quadrupled the size of your effective pixel and dramatically increased the sensitivity of the camera. But when you do that, you do it at the expense of resolution. So by going from 1x1 or just one pixel to 2x2, you've cut the resolution of the camera by a factor of 4. I have a 10 megapixel camera that I use most frequently, and when I'm in 2x2 binning, that's roughly 2.5 megapixels effective resolution, but the sensitivity is much higher. And then on the right-hand side, I show an example of 3x3 binning, and I think you get the idea. So I think of pixels as just very tiny light buckets and photons as raindrops. So if I'm looking at a dim object, the photon, which is represented by rain, is very light. And a larger bucket or pixel is much more likely to catch some photons than a tiny bucket in a given amount of time. The smaller the pixel, the longer I have to wait. In other words, the longer the exposure time has to be to catch the rain or the photons. So let's talk about equipment basics a little bit more in terms of cost. A low resolution CCD camera, like a 0.5 megapixel, costs anywhere from $125 to $200 new. The camera on the left there is a Melicam Micro EX, and I purchased mine used for $100 2 years ago, I believe it was. The high-end cameras, 26 megapixels, are about $2,000 and more, depending upon who you buy them from. Some of them can be $4,000 or $5,000. There are multiple levels of resolution and cost in between. And now I'm going to make a statement that's probably controversial to some, but I think it's true. When I was at a star party last week, and I was observing with some friends that I've known for a few years now, they showed me their eyepieces, and they had some absolutely beautiful Teleview eyepieces, Ethos, Nagler Type 31s, etc. And I asked them how much they cost, and they said they were about $500 a piece. Well, for the cost of two very high quality eyepieces, you can buy a camera that will let you see more than all the eyepieces you will ever own. Now, the caveat to that is if you own a 26-inch Dob, well, then maybe the Dob will show you just as much as the camera, but most of us don't own a 26-inch Dobsonian that we haul around in the back of our truck. So what are the challenges with this EAA? And it really depends on the equipment. On the left, you will see a fairly simple setup. And I'm going to annotate that real quick if I can do this right. This is just a one camera setup with using a refractor. And this was a setup at Okitex. And pretty much just two wires here. And then I've got a wire, you can see the wire at the bottom. It's running to my computer, and I'm running the mount and the camera from my computer. So that's pretty simple. Then you go to the setup over here on the far right, and this is my current setup, and it has three cameras. I have a finder camera, which is about 3 degrees field of view. I have a StarSense alignment camera, which does my star alignment when I first turn the mount on. And then I have a high resolution camera for the main observing and imaging. And I run all those with my computer inside my house. So the challenges are, and this is really important. I want to say it at the very outset of this slide. A lot of people get into EAA and they see pictures that other people have taken, and they get excited and they expect to be able to see something that's really high quality the very first night. That's not realistic. It takes time. The learning curve can be steep, but there are other people that have been doing it for a while that can help you. There's a lot of new terminology and technology to learn. The electronics, the cables, the batteries, the monitor, the PC, the software. It can range from a mild challenge to a real hassle, and it's best to just start out simple. Some evenings are just absolutely marvelous, and some are just very, very frustrating. But I think it's important that you learn from every experience that you have, regardless whether it's good or bad. You just learn from it, and you take that experience and you make the next one better. You can capture really high quality images with time and with some post-processing. You have to learn the camera. I know that sounds obvious, but just like you had to learn how to use your scope, you had to learn how to use a star chart, you had to learn how to use your mount, you really just have to learn the camera, what it can and cannot do. There was a time after I'd been in this for a couple of years, and to be fair, I bought some cameras several years ago, but I only used them a few times a year. So I really wasn't learning that much because I didn't use them very often. And I was frankly just thinking maybe I just ought to sell everything and go back to doing nothing but visual observing. But then one night, everything came together, and I was able to see a lot of things, to get the camera to do what I wanted to do, and my attitude changed dramatically. And the key was just being able to spend focused time with the camera over several nights. And a big motivator is just having a little bit of success. Do something simple like, put the camera and your scope on something like M13, or put it on Andromeda, or put it on the double cluster, something easy and bright, and take a picture of that or look at that. That can be a big motivator, keep you going. This last point I think is very important, and that is that, there is a lot of technology involved, and you're running software. You can be running software. You can be dealing with lots of things. And so sometimes you feel a bit disconnected from the night sky itself, you know, being outside, being in the elements. But, you know, I would say that 15 degrees temperature, 10-mile-an-hour winds, humidity, and mosquitoes can also be a distraction. So while there is a bit of a disconnect from the night sky, it also does allow you to observe on nights where you might not observe otherwise. So this is a little quiz. If you want to vote, you can. I don't really have a voting mechanism, but you can. I guess you can put it in the chat box if you want. I've got two images up here on the screen, and on the left is an image of the Lagoon Nebula, and on the right is an image of the Lagoon Nebula. One of them was taken by a very famous astrophotographer, and one was taken by me. Can you guess which one I took versus which one the famous astrophotographer took, Jim Misty? Look at the images closely for just a minute. We won't linger long, but just look. You know, each image has a lot of detail. Okay, so let's go to another image. I'm not offended. Someone says, no offense, I think yours is such and such. I'm not at all offended. Let's go to another one. I think this is a little bit more obvious. One image of the Helix Nebula is mine, one is Jim Misty's. Which one is which? Okay, I think everybody's kind of got that right, but I want you to look closely. I want you to look at the detail between the two. Clearly, the one on the right has more detail, but there's still quite a bit of detail in the image on the left. So let's go to the answer. So the one on the left was taken by Jim Misty, and he did that with a 32-inch Ritchie-Cretin custom scope with 110 minutes of exposure with an S-Big 11-megapixel camera that cost $7,000. He took this at an Arizona dark site at 4,500-foot elevation in about as dark a sky as you can get. The image on the right was taken in my backyard, which is a Bortle 9 sky. It's 15 minutes exposures and 5 minutes of processing with a camera that I bought used for under $1,000. Now, granted, Jim Misty's image is beautiful, and I am by no means saying that my image is as good as his, but I would argue there is a heck of a lot of detail in that image on the right, and it's not bad for being in my backyard with a bunch of sky glow and neighbors running their floodlights in their backyards. Obviously, the one on the left is mine. That was a 20-minute exposure, 5 minutes of post-processing. Again, Jim Misty's was through his 32-inch scope. And just to put that in perspective, my images were taken with an 8-inch Schmidt-Cassegrain. That 32-inch Ritchie-Cretin has 16 times the light gathering capacity that my scope does. And he's in about as dark a sky as you can get. And here I am sitting on the edge of the Tulsa light dome. So not bad at all. So what can affect the performance of EAA? Obviously the camera resolution, the pixel size, aperture of your scope, obviously that's going to make a difference. But the faster the focal ratio, the better. You can use focal reducers to make that happen. Some people use on their Schmidt-Cassegrain scopes, they use a Hyperstar, which can get it down to f3 to f4. Your mount tracking and how good your polar line makes a difference. There are people that use an alt-az scope, and it can work okay, but most people do better using a German equatorial mount. And I see someone ask, did I use any filters on my image? And the answer is yes. I used an Orion Sky Glow imaging filter, which cuts out most of the artificial light, the sodium vapor lamps, fluorescent lights, some of the lights around the neighborhood, etc. It still passes about 90% of the light that you desire, but it cuts out about 90% of the artificial light. Obviously, sky conditions can make a difference. Low surface brightness objects can be very challenging in my backyard and usually require much longer exposures and stacking of images to make it come together. And temperature, if you're using a camera that is not cooled, it's important to note that if you're doing this in the summertime, for every 12 degrees increase Fahrenheit temperature, the noise, the internal noise in the camera doubles. And someone may say, what is noise? Well, there's a real simple way you can figure out what noise is. Take your cell phone outside after the meeting tonight, go out into the dark, put your cell phone camera on and point it up to the sky, and you're going to see a bunch of things jumping around on the screen. That's noise. It's just internal movement of electrons within the camera itself that generate false readings, and that increases as the temperature increases. Other performance factors that are specific to the camera, obviously how long you take an exposure, the gain that you use, in other words, amplifying the signal, much like a public address system amplifies your voice through a microphone. You can use a histogram function, which allows you to clip off some of the background light, some of the sky glow. You can brighten up some of the shadow areas in an image. Binning, we talked about. Gamma is a function that corrects the non-linearity response of the camera to improve our visual perception. At its simplest form, it basically makes the image darker or brighter. And then there's stacking of images where you clean up some of that noise due to heat and some of the random noise inside the camera. It improves what we call the signal to noise ratio, and it brings out more detail in an image. And the camera that I use does stacking on the fly, which means it will stack the images as they come in, and I do not have to do it after the fact. In other words, I don't have to capture a bunch of images and then run them through a program later and stack them offline. I can do that, but the camera I'm using will do that internally on the fly. And you can apply dark and flat field correction. And very simply, a dark field is just what you would see if you put a cover on your scope and you took a snap of that with your camera. Theoretically, it should be dark. The reality is most cameras have some noise. Some of them have what's called a hot pixel, which means it shows signal even though there isn't any light hitting the pixel. A flat field is just an image of what should be an evenly illuminated surface of the same color. And the way I take a flat is I just tie a t-shirt around the end of my telescope. I point it up at the sky shortly after sundown. I take a picture. It should be a light blue, but because of vignetting and dust bunnies in my optical train and other imperfections in the optical train, it isn't. But using that flat field, the camera can then correct. It can correct for the optical imperfections so that the camera puts out a signal that is even across the entire field. So let's talk for just a minute about some of the other things regarding performance. And really, at the end of the day, it's just a balancing act. It's how good your tracking and your polar alignment is. And for those of you that are not familiar with polar alignment is just lining up the axis of your mount with the north celestial pole, which is roughly Polaris, so that when your mount is tracking a star, it is tracking at the same rate as the sky rotating around the North Celestial Pole. And a rough polar alignment, you just put Polaris in the center of the axis of your mount, but for more longer exposures, you need something better than that. And there are visual polar alignment scopes that you can do that with. There are cameras that are built just for that you can use to get a good polar alignment, etc. The sky conditions obviously make a difference. How good a tracking you have is going to put a limit on how long you can have an exposure. Light pollution filters help. We talked about that a minute ago. And off to the side, there's an image of what I'm using now in my setup. The camera settings themselves, the exposure time, you can shorten that with more gain, but as you use a higher gain, you get more amplification of noise. And by stacking images, you can get a much better image of a dim object. You have to have a good focus. A Bahtinov mask is really important, and all a Bahtinov mask does, it's something you put over the aperture of your scope, and it creates diffraction spikes, and you just adjust the focus so that the main diffraction spike shows up right in the middle, in between these other diffraction spikes, right there. So if the diffraction spike was over here, it's clearly out of focus. If it's over here, it's clearly out of focus. What we want is right there in the center, right there. And some of you may be thinking, boy, this is more like astrophotography. Well, it is and it isn't, because I'm not doing hours and hours or days and days of taking images. I'm doing this in 10 minutes, typically, or less. Okay, so here are the cameras that I have. I have a Metal-Oxide Micro. It's basically a repurposed surveillance camera. It's a 0.5 megapixel resolution. It's a very small sensor. You can go up to 17 seconds of exposure. You don't have to have a computer to run it. Let me annotate this real quick and I will show you. If you look on the back, there are some buttons right there that access an internal menu of the camera. So it's fairly inexpensive. You can buy these new for $130. I paid $100 used for this on cloudy nights. On the right-hand side is a better CCD camera. It's called a Metal-Oxide Extreme. It's extremely sensitive. It will bring an image up very quick, but the resolution is only about 0.4 megapixels. So it's got big pixels, low resolution, but it will go up to an hour of exposure. It is a cooled camera. It has an internal thermoelectric cooler that will cool it down well below ambient temperature. And these cameras, you can buy these used on cloudy nights for $600 to $800. Brand new, they run about $1,400. The other two cameras that I have a Metal-Oxide Universe. It's a 6 megapixel CCD camera. It does have a cooler, and it will cool to 80 degrees below ambient. So for example, if I went out tonight and used it, it would cool the camera down to about 15 degrees below zero. It does require a PC to run it. I've seen these on cloudy nights recently for $600 to $800, and brand new, they're $1,900. The camera that I'm using the most lately is the Metal-Oxide Skyraider. They call it the DS10C Tech. Basically, that just means it's a 10 megapixel camera, color, and it's thermal electrically cooled. It's a CMOS based camera. And I like this camera very much. It's very versatile. A lot of the images I'm going to show you here in a few minutes were taken using this camera. It can go up to 17 minutes exposure, but I've never found it necessary to go longer than a minute to get what I want. It does come with software that will do frame stacking on the fly. It will do dark and flat frame correction on the fly. It's a great little camera. I really like it a lot, and hopefully you'll see why in just a few minutes. So this is my current setup. We talked about it a little bit earlier. You know, I have seen much more sophisticated setups than this, but this is what I've kind of gotten to, and this is about as far as I want to go. I've got this small Metal-Oxide micro, which I'm using as a finder scope. It gives me about a 3-degree field of view. I use it for a finder. You know, you salute an object, and sometimes it's on the edge of the field of view of the main camera, but you can see where you are, and you can basically use that finder camera to star hop where you need to be if you're tracking or your go-tos are off a little bit. Then I've got the star sense aligned camera that's only used to do a star alignment at the start of the night. Then this is the Metal-Oxide DS10C Tech. And you can see down at the bottom, you've got my batteries, my control box, and we'll talk more about that in a minute. I've got a 50-millimeter guide scope that I'm using with that micro. I've got an AVX mount, and you can buy those used on Palladium Nights for about $600. I built a homemade rolling tripod that's made out of just scrap lumber. It's got locking casters on it. I can roll that scope out to a predefined place on my patio, lock the casters in place, look through the polar alignment scope, make a few turns of the screws, and I'm pretty much polar aligned. It might not be exact, but it's pretty good. I also am using a Feather Touch focuser with a micro touch motorized focuser, so it has remote focusing on it, and it's temperature compensated focusing for the mirror aspect of the Schmidt-Cassegrain. I also have dew heaters on the scope, on the guide scope, and the cameras, because I have had several sessions earlier this year in the spring where I thought, man, that image looks kind of goofy. What's going on? And I went outside and my scope was completely fogged over. It was amazing I could see anything, but it sure can screw up a night of taking pictures if you're not careful. So this is my current setup, a little bit more detail. On the left-hand side, you'll see my control box. In this storage container that I bought from Walmart for about $8, I've got inside of that 2 remote powered hubs. I have some of the electronics that the cameras are coming into. I've got cables that are connecting and going back to the house. I've got 3 batteries. I've got a battery for the camera, a battery for the mount, a battery for the dew heaters. If you look at this image in this picture in the middle, you'll see this is a locking caster. And if you look closely, you'll see masking tape on the patio. That's where I roll my scope out, put it in a predetermined spot. The scope's already pre-leveled. I look through the polar alignment scope right here, line it up on Polaris, turn on the StarSense alignment camera, and in about 15 minutes after rolling out my scope, I can be observing. These cables that you see right here are coming over here into my house, and they go through a PVC pipe that I had a contractor put through the brick wall. And that pipe is big enough for me to run 2 control cables through. And that connects to my laptop inside and my big screen TV. And that's what it looks like inside. I've got my laptop. I've got my big screen TV. Somewhere there's something cold to drink, and I'm out of the elements. I'm either comfortable in the air conditioning or comfortable in the heat. I don't have mosquitoes dive bombing me, and it's a lot of fun. And probably one of the best things is my wife knows where I am, and she knows when I'm coming home because I'm already home. So here's my laptop. Here's my big screen. Here's the Ring Nebula. And from this laptop, I can run all the cameras. I can run the main CMOS camera, the CCD camera, the focuser, and I'm using SkyTools 3, which is an interactive star chart for my go-tos and picking my objects. I like SkyTools very much for planning my observing sessions. It's a very powerful tool. It's a little complex, a little hard to learn initially for me, but it's a pretty good setup. So I'm going to show you some sample images, and we're going to start first with the Extreme. It's a 0.4 megapixel camera. This is an image of the moon, obviously. Just let you look at that for a second, and then I'm going to go to the next camera, and you can see the difference. This was a 5 millisecond exposure. Okay, this is a 5 millisecond exposure with the Metal-Oxide Universe. It's a 6 megapixel camera. You can see a lot of detail in this, a lot of detail. And then this is a zoomed in area of the moon. And I took about 30 seconds of video of this, and then I stacked it in Registacks, and pretty good detail. I think if I were to do this again, I could probably do a better job yet. So the camera is very versatile, and I think you'll see that in the next few minutes as I go through some of these images. So this is Andromeda M31, and this is from that Metal-Oxide Micro. That's a $100 camera. I know it's not anything that Sky and Telescope is going to print, but if you think about it, that's about as good as some of the image you would see in books 30 or 40 years ago. I'd like to point out just a couple of things. I think this is M110. I believe that's M32. And if you look closely, you can see some of these dust lanes in here in Andromeda through here. Now this is Andromeda from the Extreme, so you can see a lot more detail, but this is still a low resolution camera. It's about a little under 0.5 megapixel, a little bit grainy, but still very sensitive. You can see some of the dust lanes in this right through here. You can see some of the dust lanes up in here and in here. Very sensitive camera, very fast. And this is Andromeda from the 10 megapixel camera. You see a lot more detail with this. And all these images that I'm showing you were taken from my backyard. Some of them on a night when the moon was half full. So I'll let you look at that for just a minute. You see all this detail through here, some detail in here. These dust lanes up in here. There's some dust lanes in here. This is the Orion Nebula. This is from the Extreme 0.5 megapixel camera. Not super high resolution, but still, it's a nice view. A lot more detail than I can see through the eyepiece. Some people might be able to see that in a big daub, but with my scopes, I can't see that level of detail. It is interesting to me that you can see the trapezium right there. You can see the dark dust lanes on the backside in here, this dark area. This is Orion with the Universe camera, 6-megapixel camera. There's no stacking or processing or anything. This is one 45-second exposure, and you can see kind of the downside of a single exposure, long exposure on a bright object like this is you blow the core out. But there are techniques that you can use to correct that and still show the trapezium, and I'll show you that in just a minute. Now this next is from a 10-megapixel camera. I think I could do a better job on this now, but this was my first attempt to capture the Orion Nebula and not blow out the trapezium. And if you look, you can see the trapezium right there. You can see you can see the 4 stars. I know there's 5 or 6, but you can definitely see 4. And you can see some nice detail back in here and out in here and out in here, etc. And I think I'll show you another picture of Orion here in a little while. That's I think is better. It's better mainly because I've learned how to better use the camera. So these images I'm about to show you are all from my backyard. Again, I live 1 mile east of a super Walmart, a Lowe's, a Reese's, a Costco, several car dealerships about 1.5 miles, 2 miles away, Bortle 9 sky. So here's the Ring Nebula. You can see the central star in there, and I don't remember what magnitude that central star is. I think John knows. It's pretty faint, but you can see it. And this took about 10 minutes. Now you can see the ring and you can see some detail within seconds, but to see the central star, it takes longer because you have to stack the images to see that central star. This is the Dumbbell Nebula. I don't think I've ever seen that level of detail from an eyepiece. Now, maybe some people with a huge job and lots of patience have seen it, but I haven't. But again, everything I'm showing you is from my backyard. The earlier images were just to show you the differences in what the different cameras can do. This is all the images I'm showing you now are from the 10-megapixel camera. This is the Trifid or Trifid Nebula in Sagittarius. You can see the emission nebula on the left and the reflection nebula on the right. Again, from my backyard. Fortunately, the sky glow to the south is pretty nominal. Bixby's not known to be a super bright area, and I live right on the edge of the city limits of Bixby, Tulsa, and Broken Arrow. I live at about 111th and Mingo. So this is the Eagle Nebula, and it's a very beautiful object. Interestingly enough, I thought up until the time that I prepared this presentation that it was in Sagittarius. It's actually in Serpens, just above Sagittarius, but I always think of it being in the region of the teapot, so I just thought it was in Sagittarius. And if you look carefully, you'll see Mr. Eagle right there. Some nice detail in there. If I am not mistaken, this is somewhere in here is what they call the pillars of creation. I don't know if it's in here or over in here, but a lot of nice detail in this picture. Again, backyard, 10 minutes. This is the lagoon. This is just a wider field view of the same thing I showed you earlier when we were comparing Jim Misty's 32-inch captured image over 110 minutes versus my 10 or 15 minute with my 8-inch scope. And this was taken in the backyard. There's a lot of detail in this. I think it's a pretty image. I like it. So, and this is M13 Hercules globular cluster. And it will, if you're patient and play with the exposure, you can, I don't know if you can resolve it all the way down to the core, but you can definitely see a lot more than you can see in a scope. This is the Crescent Nebula. And many times I have slewed my telescope with my eyepiece to that area of the sky, and I have never seen it through an eyepiece, not once, especially from my backyard. What's so fun about this camera is there are lots of things that when I first got this go-to telescope many years ago, I'd say, okay, what's the North American Nebula look like? What does the pinwheel look like? And I would slew to it and I would see absolutely nothing in the eyepiece. But with this camera, I see things I would never see otherwise from my backyard. This is part of the veil. I believe this is the eastern veil, if I'm not mistaken, in Cygnus. There was no oxygen filter on this. This was just the sky glow filter. And this is the Cat's Paw Nebula in Scorpius. And what's interesting about this image is that it was taken at about 15 degrees above the southern horizon. So it's going through lots of air mass and still was able to pull out some nice detail of this fairly dark object. And this is the Needle Galaxy. And if you look closely, you can see some detail in this. You can see the central dust lane through the bulge. You can see this little star here right above the top of the central bulge. You can see this little guy. And again, this was in my backyard. I would never see that through my scope with my eyes. I would see something. I would see a faint streak, but I wouldn't see all that detail. This is M101. There's some vignetting in this picture. This was taken several months ago, earlier this year, when I was still learning the camera and I didn't have my focal reducer dialed in to the proper spacing. But nonetheless, detail I wouldn't have seen otherwise. And this is the Whirlpool Galaxy. And it's interesting because this is over the big light dome over the city of Tulsa. Now, I think when I took this one, it was fairly high up in the sky, maybe 60 degrees or so, but still have a hard time seeing that through my scope in my backyard. This is Comet Neowise. I took this from my backyard. I wish that I had a much wider field of view and I could have taken something to see the long tail. That I saw some really nice pictures posted on the club newsletter, but this was a 10 5-second images stacked from my backyard. And I think this is the last image I'm going to show, and this is just it's a collage of the transit of Io and Ganymede across Jupiter and the Great Red Spot. And this was, I think, the second weekend in August. I think it was August 14th. It might be off a day or two on the actual date. But if you look very carefully on this image over here at the far upper left, you'll see a little moon right on the limb of Jupiter. There's another little moon right there. You can see a shadow. So there's a moon between us and the sun here that's transiting. There's the red spot. And you can see the progression. And now that moon that was on the limb, when you get to the third image going down to the right, now it's casting its shadow. The first shadow has moved over. The red spot is moved, and so on. And then this was taken over about an hour, about 2 hour period, if I'm not mistaken. What's interesting is that Jupiter does a complete rotation in 10 hours, so it rotates very fast. And the way I captured this was by using the video aspect of the camera. I actually took about, I think it was a 90-second video, and then I ran the frames through two freeware programs, one called AutoStacker, the other one called Registax. And when you look at the video, you just see this planet kind of jumping around in the image and looks kind of wobbly and wavy. And when you run it through AutoStacker, it picks the best frames, the ones that you're lucky enough to get a good shot of, and it will pick the best frames that you tell it to, like the best 25% of the frames or 15%. It then stacks those. You get a higher signal to noise ratio, and then you apply what's called a wavelet processing in Registax, and you can bring out the detail. Before I did this, I could see some faint bands. I could not see the red spot, and I sure couldn't see these shadows. But after doing this processing, which took about 15 minutes, you could see all this. So it's pretty cool stuff. So here are some resources that I talked about earlier. There's a guy named Jim Meadows. He's got a website called remotevideoastronomy.com. It's very informative. A lot of his ideas were very helpful to me in setting up my current equipment that I'm using. There was a recent article in June, Sky and Telescope, written by Rob Melise, exploring the deep sky with video. It's very good. There's some resources at aginaastro.com. It's one of the many astronomy equipment vendors out there. There's a site called liveskies.org, and it is a site where you can go out there and watch people doing live observing sessions with Malin cams, and you can watch how they're using their camera and what they're looking at, etc. And you might recall earlier in the presentation, we talked about being able to do spectroscopy, emission line, absorption line analysis, redshift analysis. This site, rspecastro.com, is where you can buy the diffraction gratings and the software to do that. With that, I believe I want to go over just very quickly. I did mention nothing but Malin cams in the presentation. There are other manufacturers besides Malin Cam. There's Revolution Imager. John Land owns one of those. There's QHY, ZWO, Omega, Orion, Celestron, Starlight, and there are others on top of this. So there are many choices out there. If you go on cloudy nights, you'll see a lot of imaging cameras. If you're interested in going into this part of the hobby, make sure you're getting a video camera. So with that, I will open it up for Q&A, and you're welcome to send me your questions via chat or turn on your mic. It's up to you. Okay, so have I considered doing live EAA broadcasts for Astronomy Club of Tulsa members? I have talked about that a little bit with John Land, but I haven't discussed it with Tamara or anyone else in the club, but that is something I would like to do. There's some software that I need to install on my computer to make that happen, and I need to practice a little bit with it before I do that, but certainly that is something I would like to do. So, James, if you want, why don't you unmute everybody and then people can just ask questions over their mic if they'd like to.
Sure. Let me hear this. I've never tried to do a mass unmute. I will try it.
Can you zoom in on an image? Yes, you can. Absolutely. And I do that frequently.
Well, I'd just like to thank you for your presentation. It was pretty good.
Thank you. Thank you. I appreciate that.
I really enjoyed it too. This is something that I've actually been kind of messing with for about the last year. I'm kind of in the same boat where I'm not going for, you know, award-winning photos that I spent days processing. I just want to see more than what I can see through the eyepiece. And so that's, my equipment's still not quite as put together as yours is. But just from what little I've gotten, it's amazing what you can see with just a few seconds of exposures versus what you can see through the eyepiece.
Yep, you're right. You're right.
Hey,
Go ahead.
hey, Robin, it's Michelle.
Hey, Michelle, how are you?
I'm doing good, thanks. Just a curious question on your setup that you have there at your home. How much did that cost you to start that up or to put that together ish?
Well, if
Or the
everybody
setup
wants-
that you had or the one that you had at the star party?
the one that I had at the star party, let's go to that. Let me go back. Okay, so we're looking at this setup on the left here. And I was using this past week, I was using this Explore Scientific refractor. I already had that before I got into this. The camera that I was using this past week was the Metal-Oxide DS10C Tech. I bought that used on AstroMart for $950. And then, of course, you had to have a laptop. Most people already have one. The first laptop I bought to run my cameras, I bought at Best Buy brand new for $200. But I found it worked fine as long as I was only running one program. But then when I ended up running two cameras, a remote focuser, and mount control, it kind of overwhelmed the $200 laptop, and I had to buy a little more expensive laptop that I think was $500. But for, you know, you can start out with something like I was using last week, assuming you already have the mount and you already have the telescope. You know, I would say between $1,000 and $1,300 or $1,400. But you don't have to start there. You can start with a lower resolution camera just to make sure that you like it before you really dive into the deep end. You don't have to go big right away. So let me answer some of these other questions. But before I do that, Michelle, was there any follow-up on that?
Nope, that's about it.
Okay, thank you.
But
So
nice pictures.
thank you. Thank you very much. So Brett Emerald says, I've done this before in a limited capacity with a DSLR and a T adapter. Any particular reason you go with a video version instead? Well, I would say probably because I didn't own a DSLR camera to begin with, and I wanted something that was a little more plug and play, if I can use that term. DSLR is not really, I know you can see the images, but I'm not aware of any software that you can see it in near real time. With this, you can see an image in seconds. It might not be something that you'd be proud to frame and hang on your wall in your office or anything, but you can see the object. And, you know, if you want to stack it, you can clean it up, but you don't have to spend minutes to see something. You can see something in seconds depending on the object. So that's the reason I went with video. I didn't own a DSLR camera and I wanted something that would, I could see on my computer screen. Yep, I see someone's already ordered a video camera and they're going to go down this path. I hope I can help you with that. I think the ZWO may have its own software. A lot of people use something called SharpCap. So, see, my wife asked, were all the images in the backyard stacked? I would say all of them except the moon were stacked, and the number of images stacked ranged from 10 images up to 30 or 40, and most of them anywhere from 15 to 30 seconds long. And the camera does produce the colors. These are not false colors. This is color produced by the camera. So you can tweak the colors in the image with light curves if you want, but when you do that, you tend to mess up your background, the black background. So you have to be careful what you do with that. Some people use these cameras to do full-blown astrophotography, and they'll take narrow band pictures. They'll take images through 3 or 4 filters. They'll put them through PixInsight, Photoshop, AstroPixel, you know, whatever, and spend hours and hours and hours and turn out really, really, really nice stuff. So, okay.
One thing I wanted to mention is there's a device that I've been using there are a couple actually that are on the market right now that are actually specifically designed for electronically assisted astronomy. The one I use is it's a Stellina smart telescope. It's basically got all the different bits and pieces that's all kind of in one little package, and you just take it out and you set it up and you control it with your iPad. Now, it's not as precise as a lot of the instrumentation that you have. I think its maximum is, 6.5 megapixels, and it's only got I think a 90 millimeter refractor. But there's another one out there that's called the EV scope. That's about a 4-inch Newtonian that does the same thing, where it's got the camera and the software all kind of built into it. Now they don't have as much degree of freedom. Like, you can't adjust a lot of settings. You basically just have to take whatever it gives you. But it's kind of a quick and dirty way of getting a lot of this stuff. And the technology, I think, you know, the ones that are out now, they only just came out. And so it's likely in the next 10 or 15 years, we're hopefully going to be seeing much more advanced ones that have more of the options. But that's just another thing that people can try.
Right, right. I've seen some write-ups on these out-of-the-box imaging telescopes that have the camera and everything built in. I kind of like the flexibility of the cameras that I'm using, especially this 10 megapixel camera. You can do planetary, you can do deep sky, you can do wide field, just a lot of neat stuff. So
yeah, there's a lot more, I'd say, because like what I've worked out is, after using the Stellina for probably about a year now, is that I'm actually starting to kind of go back to using my regular astro imaging cameras. Just because of the options, because like with the Stellina, you can't do planets, and there's a lot of stuff that would be really nice if you could just throw a filter in there. You can't throw a filter on it. So there is a lot more that you can do with that kind of setup. I agree.
right, right.
Hey, Robin, this is Sven. I've got a quick question. So towards the beginning of your presentation, you mentioned a term, something like lucky imaging.
Yes, yes.
Could you explain that?
Yes, if everybody won't get seasick as I go to the end of the presentation, I will. Okay, so I'm not sure if I can do it. Let me see. I might be able to.
Can you make it bigger on the screen? And we just got a little square.
Yeah, give me just a second. I'm gonna
I
do
did it
something.
myself. Never mind.
Give me just a second. I'm gonna do something here. Okay, so let me. Okay, bear with me. I am not leaving y'all in the dark on purpose. I'm going to share a different screen. So can everybody see that? It's kind of a blurry image of Saturn.
Yeah.
All right, so this is a video I took of Saturn. Now I'm going to play it, and I want you to look at what happens to this. I'm gonna zoom in a bit more. John asked, can you zoom in? Okay, this is a video that I took. Now I want you to look at Saturn. You see how it's moving around?
Atmospheric distortions?
Exactly. Exactly. And so the way I explain atmospheric distortions, I like simple explanations because I guess things have to be broken down to its simplest terms for me to understand them. So if you think about it, if you're standing by a stream that's flowing and you're looking at fish in the stream, you can see the fish, you can make them out, but you can't see a lot of detail about the fish. But if you're looking at fish swimming in a still pool of water, you can make a lot of detail out. And the whole difference is the movement of the water between you and the fish. Well, the atmosphere is moving as you're taking this image. I'm going to just play it again. And so the lucky imaging concept, what it does is you take this video and then you run it through a program called Auto Stackert, and it picks the best images. In other words, the ones that you were lucky enough where the seeing steadied for just a moment, or you happen to just catch the planet at just a good moment. And it takes those lucky images, in other words, the best frames, and then it stacks them to produce a better image. That's what Saturn looked like before I did it. Let me see if I have one of, let's see here. Let me see if I have one of, bear with me for just a minute. If I have one of, let's see. Well, I don't want to waste y'all's time. You get the idea. You can see how this moves around. So Lucky Imaging just analyzes it frame by frame, picks the best ones with the least distortion, stacks those so that you get a better signal to noise ratio, and then you get a better image. So
Thank you.
that's probably a long-winded explanation, but that's the best I can do. So.
If I could break in for a moment, and I want to address a comment that Brett Emerald made about using a DSLR. And he says the disadvantage of a DSLR is you have to wait till the next day to see if you got anything. My comment to that is oh, honey, you should have tried this during the days of film photography.
Well, you can see some things on your little screen on the back of the DSLR. I've seen people doing that out at Okie-Tex and out at the observatory. So you can see some things, but as far as seeing a nice big image on a computer screen, maybe there's some software you can use to see that. But I think if I'd had a DSLR camera, I probably would have started with it rather than these made for purpose cameras. So.
There is software that will allow you to do that. Backyard EOS and Backyard Nikon is one, and there's another called, I forget what it is. Hang on a second, I can look at my desktop because I got it sitting there. It's called Digicam Control. And it will give you an image of what you're seeing on the screen, and it will also allow you to control individual exposures. We'll show you those once they're complete. And I think it'll do live stacking. I don't remember for sure. I haven't used that.
Right. Can everybody see this picture of Andromeda?
Yes.
Yes.
Okay, this is an image I took this past week, and it's actually two images stitched together. And this is a total of it's like 20 minutes exposure for each panel, and there's two panels, so this is about 40 minutes of exposure. And you can see a lot of detail in the dust lanes and see the two satellite galaxies. So
That's amazing.
That is.
Before we go off, can everybody hear me?
yes,
I can hear
sir.
you.
I know everybody's enjoyed the presentation. Send us some feedback on your response about doing this on a weeknight. We chose a weeknight because we seem to have conflicts on Fridays with family activities, sports, and people being out of town. And so we thought we'd try a Tuesday or Monday or a Tuesday, depending on what our speakers can do. So we've got a speaker on Monday, the 26th. His name is Dr. Aaron Corner. Some of you know him. He was actually an officer in the club when he was going to TU. And he has a doctorate in solar physics. So he's going to talk to us about the Parker Space Probe, and I forgot what the other one is that's up there. But that'll be coming up next month.
Hey, Sven and Michelle, your dog is adorable.
Thank you.
What's his name?
Oh,
Her name is Kita, and she's a little Pomeranian Chihuahua mix.
Oh, she's adorable.
She was at the star party with us.
Oh, she's cute.
Not at all spoiled. Not at all.
No, no.
Oh, I can tell she's definitely not spoiled.
Yeah, we had her all bundled up, and she slept in her wagon with the little down blankets
Oh,
in the field.
Well, that's all I had. If there's any other questions, you're welcome to, you can send them to John and he'll forward them to me, or I can give you my email address offline or whatever. But it's a lot of fun. I enjoy it. And
I'll send out that list of resources on an email. And I think James will have a link to the recording for it. So people that didn't actually get to be online can look at it later. So
Yeah, hopefully we'll have that up here in an hour or so. It normally takes a little bit for it to get finished processing.
Nice presentation, Robin.
thank
it was a
you.
very good presentation. Thank you.
Thank
Showed us some
you.
really nice
it's
pictures.
awesome.
Thank you.
Good night, all.
good night.
Right.
Good night.
Bye.
Thank you for the
Thank you.
presentation.
Yeah.
Yep, thank you for inviting us.
participating.
Yeah,
All right.
thank you very much.
Bye-bye.
Okay, thank you all for participating. We hope that you will join us for our upcoming events. Please give us your feedback on what you thought about tonight's meeting. Any ideas on how we can improve your experience will be welcomed. You may email me at astrotulsa.prez@gmail.com with any questions, comments, or ideas. And again, thank you for your participation and welcome to the club.
Thank you.
Thanks, Tamara.
Bye,
Thanks a lot.
Sven. Bye, Michelle.